Hope you're having a productive day. In this video, we will be working through another past paper question from the physics subject. This is going to be question number 4 from the 2014 physics paper 2. So without any further ado, let's get right into it. This was the first question in section B for the 2014 paper 2. The question is divided into 3 basic sections, but they're very similar sections to each other. They're all related, really. So the first question asks us to explain why a particle moving with constant speed along a circular path has an acceleration. All right, this question doesn't require much working out or calculation. This is just something that you would write out, okay? It would be a statement. So an object, or a particle in this case, has an acceleration when its velocity is changing. If an object is moving at constant speed, that means that the magnitude of its velocity is not changing. But if it's moving in a circular path, the direction that the particle moves in is constantly changing because it's moving in a circular path. And because its direction is constantly changing, its velocity is constantly changing, even though its speed is constant. So because its velocity is constantly changing, then the object has an acceleration. Next question. The value of radial acceleration is given by the expression v squared over r, where v is the speed and r is the radius of the path. Using base units, show that this expression is dimensionally correct. So this is going to be some dimensional analysis, and it goes as follows. The first thing that you're going to do is write the dimension or the units for acceleration. So the units for acceleration, A, is meter per second squared. That's the unit for acceleration, meter per second squared. Now, from the information that they gave us, they said that centripetal acceleration is v squared over r. So we are going to have to find the units of centripetal acceleration, which is this, and we're going to have to see if the units match up with this over here, which are the units for acceleration. If the units for centripetal acceleration match up with the units for regular acceleration, then it means that centripetal acceleration is indeed acceleration because it has the units of acceleration. What would be the units for this equation here? Well, velocity has units of meters per second, and it's squared, so we're going to have to square this portion up here. Radius is going to be a distance, so it's going to have the units of meters. When we square, we're going to take the index and multiply it by the index of the individual terms. So the index for meter, even though it's not shown, the index is actually 1. It's m to the 1. So m to the 1, 1 times 2 out here, since we're going to multiply the index by what's outside the bracket, it would be 1 times 2, so it would be 2. So that would be the unit there for the meter in the numerator. Now we have the second. It's the same procedure. We're going to take the number outside of the bracket, or the index outside of the bracket, and multiply it by the index for the variable inside the bracket. So it's 2 times minus 1. That gives us minus 2. So we are left with meter squared per second squared. We can rewrite our denominator, which is m. Here we see that the meters in the denominator cancels with one of the meters in the numerator. The reason that is so is because meters squared is basically meters times meter. And then we have meter in the denominator. If we do this, we remove a meter from the numerator and we're left with just meters. So basically when we have meters squared and we have meter here, we can just say meter cancels with that square, so we just have meter. And then we are going to get meter per second squared. So we see that v squared over r, when we work out the units, gives us meters per second squared, and the unit for acceleration is meters per second squared. So these two things are indeed the same. Hold on, let me zoom out a little bit so you can see it. Yeah. So these two up here and down here are the same, which means that this is actually acceleration. Now we move on to part B. A racing car of mass 500 kilograms starts from rest and accelerates at 6.0 meters per second squared along a straight horizontal road for a distance of 150 meters. It then enters at constant speed a horizontal circular curve of radius 200 meters. What is the magnitude and direction of the resultant horizontal force acting on the racing car while it is traveling around the curve? Now, one thing that I haven't been doing in my videos too much is I haven't been necessarily writing down the information that the question gives us. And the reason I am not doing that is because I have pre-worked out these questions before. So I kind of know what goes where. When you know the units and you know the formulae, you can easily just slot in the proper numbers where they're supposed to go in a formula. But if you're not too familiar with all of that, then you might gain some benefit from writing down all of the numerical information that is given to you in the question. For example, you could say mass is equal to 500 kilograms. You would write that down. Acceleration is equal to 6.0 meters per second squared. You would write that down. The horizontal road has a distance of 150 meters. You would write that down. And then it enters at constant speed a circular curve of radius 200 meters. So the radius of the curve is 200 meters. You would also write that down. So you write down those kinds of bits of information so that when you're working out, you know what numbers are supposed to go where. Moving on into the question. What is the magnitude and direction of the resultant horizontal force acting on the racing car while it is traveling? Well, this is asking for magnitude and direction of a resultant horizontal force. Now, the horizontal force that is keeping the car or that is guiding the car around the curve is actually the centripetal force, right? And that centripetal force has a magnitude and a direction that we are going to find out right now. Centripetal force, we can call it Fc, has a magnitude of m times v squared over r. And you see the v squared over r come back. The v squared over r was actually centripetal acceleration. Now, according to Newton's second law, force is equal to the rate of change of momentum, or in simpler terms, force is equal to mass times acceleration. So the centripetal force only exists when there is a centripetal acceleration. So the centripetal acceleration, v squared over r, is the acceleration that we're going to use, and then the mass is going to just be mass, okay? So the centripetal force is the mass here times the centripetal acceleration here. So that's where we get mv squared over r from. Now, in order to find out the centripetal acceleration, which is the resultant force in this scenario, we need to find the mass, the velocity squared, and the radius. Now, if you wrote down the numerical data that was given to you, you would know what the mass is, 500 kilograms. You would know what the radius is, 200 meters. But we don't get v. What is v? V is linear speed. We did not get that from the question. So how would we find the linear speed from the question? Well, you would have to use kinematics because the question gave you some other information. So you would need a kinematics equation that incorporates linear speed, acceleration, and displacement, because those were the different quantities given to you by the question. Now, what kinematics equation would do all of that? The kinematics equation that we would use would be v squared is equal to u squared plus 2as. Now, you would want to find velocity, right? That's what this v is. But you don't need velocity to figure out this question. You actually need v squared. Now, you could easily just find velocity and then square it, but you would just be doing extra work because you already get v squared over here. So all you need to do is just take the answer from this side of the equation and put it as v squared, and then take that v squared value and put it here. And it's very simple when you do it like that. Now, the car started from rest, so u is 0. U squared is also 0, since 0 times 0 is just going to give you 0. So what we really have is v squared is equal to 2as. here we can just solve what v squared is. So v squared would be 2. The acceleration is the acceleration that the question gave us, which was 6 meters per second squared. And the distance that the car accelerated for in the straight path would have been 150 meters. Now, the acceleration that the car has in the straight line is going to give you the final linear velocity that the car has as it enters the bend. So that's what v squared is going to be. V squared is going to be the square of that velocity. So when we have v squared, we're going to get 1800 meters squared per second squared. Now that we have v squared, we can just put it in this equation. Now we can rewrite the centripetal force, which is the resultant force in this case. And that's going to be the mass, which was stated to be 500 kilograms, multiplied by v squared, which we just calculated to be 1800 meters squared per second squared. And then we're going to divide that by the radius, which was stated to be 200 meters. So when we have done all that calculation, we should end up with a force of 4,500 newtons. And again, I did not include the units here because I'm trying to save space. But if you wanted to include the units, you could. And ensure that your final answer has the correct unit, or else marks will more than likely be deducted from you. The question also asks us to find the direction of the resultant force. Now, centripetal acceleration acts towards the center of the circular path. It stands to reason that centripetal force, which comes from centripetal acceleration, also acts in that direction. So the direction that the force would act is towards the center of the path. We're finished with part B. Now we move on to part C. A stone of mass 500 grams is attached to a string of length 50 centimeters, which will break if the tension exceeds 20 newtons. The stone is whirled in a vertical circle. The angular speed is slowly increased until the string breaks. Draw a diagram to show the forces acting on the stone in a vertical circle when it is at its highest point and its lowest point. So this question wants us to draw some diagrams. Then the question asks, in what position along the vertical circular path is the string most likely to break? Suggest a reason for your answer. And then it asks, at what angular speed will the string break? Now, the question says spring right here. The question says spring, but this is a typo. It should be string. Now we're going to draw diagrams to answer the first part of this question. Draw a diagram to show the forces acting on the stone in a vertical circle when it is at its highest point and its lowest point. Let us assume that this is the center of the circular path that the stone takes as it is being whirled in a vertical circle connected by a string. Now it wants us to draw diagrams at the highest and lowest point. At the highest point, the stone would be up here. So this now is the stone. We need to find the forces acting on the stone at this point in its motion. The two forces acting on the stone would be tension force and then the stone's weight. So these are the two forces that are acting on the stone at its highest point in the vertical circle. Now we need to draw a diagram showing the stone at its lowest point and the forces that are acting on it. So basically that would look like this. This would be the lowest point, and the forces acting on the stone would still be tension. And now the weight of the stone, mg. So these are the two diagrams that you would need. If you wanted to, you could also extend and say when the stone is at this position, has a tension, and its weight acts downward. And you could also extend out here and say when the stone is at this position, it also has another tension, and its weight also acts downward. In this scenario here, the only force acting to keep the stone in the circle, or the only force pulling the stone towards the center of the circle, is tension. And it's the same over here. But up here, the force that is acting to pull the stone towards the center of the circle is the tension and its weight. Down here, tension and weight are also acting in the plane that pulls the stone towards the center of the circle. And by the way, I don't know if I've mentioned it yet, but centripetal force is the force that is going to pull you towards the center of the circular path, which is why you constantly change direction, because you're constantly trying to go towards the center of the circle. So these two down here and up here would answer the question, but I included these two because it will help us to answer the other parts of the question. In what position along this vertical circular path is the string most likely to break? Suggest a reason for your answer. The forces that are acting to keep the stone moving towards the center of the circle vary depending on where in the circle you are at. At the highest point, the forces are the tension and the weight. At the sides, directly at the sides, it's just tension. Weight doesn't have anything to do with it because it's acting at a right angle, so weight has nothing to do with this force here. And at the bottom, tension and weight are involved again. Now the string will break when the tension exceeds a threshold. The question stated that threshold as 20 newtons. So when the tension is high and it exceeds 20 newtons, then the string is most likely to break. So in which one of these scenarios is tension largest? We have tension here, we have tension here, we have tension here, and we have tension here. But which one of these tensions is the largest? Because that's the tension that the string is most likely to break. Well, here, the tension is just going to be equal to the centripetal force, which is mv squared over r. Here, the tension is also equal to the centripetal force, mv squared over r. So these two tensions are the same, right? So when the stone is at the sides, tension is equal to mv squared over r. This is when the stone is at the side. So I'll just call this sides, right? Now when the stone is at the top, tension plus mg gives you the centripetal force. So at the top, tension plus mg is equal to the centripetal force. So tension then is equal to the centripetal force minus the weight, which is mg. So that's at the top. So already you can see tension is equal to mv squared over r here. All right, let me just write it down here as well. So centripetal force is mv squared over r. Here, tension is equal to mv squared over r. Here, tension is equal to mv squared over r minus mg. Something is being subtracted from mv squared over r, which means the tension here is going to be less than the tension at the sides, according to these two equations, right? Now let's go to the bottom. At the bottom, tension minus mg is equal to the centripetal force, and it's minus mg because mg is acting in the opposite direction of the tension. It's acting in the same plane but the opposite direction. Up here it's acting in the same plane but in the same direction. Because it was acting in the same direction, that's why we get t plus mg. But here it's acting in the opposite direction, so t minus mg is equal to the centripetal force. In other words, tension is equal to the centripetal force plus the weight. So it's equal to mv squared over r plus mg. We already said that the tension here would be larger than the tension here. But what about the tension at the sides compared to the tension at the bottom? Well, here it's just mv squared over r. At the bottom, it's mv squared over r plus mg, which means at the bottom, the tension is even larger than at the sides. So if we're supposed to compare it, the tension at the top would be smaller than the tension at the sides, and then the tension at the sides would be smaller than the tension at the bottom. So which one of these is tension greater? It would be the tension at the bottom. And that is the explanation. It's longer, but you don't have to include the sides. The sides are there to help to understand, but you could just say the tension at the bottom is, you could just say the string is most likely to break at the bottom because tension is greatest at the bottom. And then you could say the tension is greatest at the bottom because of this equation, because of this little working out here. T minus mg equal fc, and then T equal fc plus mg, and mv squared over r plus mg is equal to T. So you could just say that. Now the question goes into one last part. It says, at what angular speed will the string break? It says spring, but it's supposed to be string. At what angular speed will the string break? Let's figure that out right now. How would we find the angular speed at which the string would break? Well, remember at the previous part of the question, we said that the string is most likely to break at the bottom. And at the bottom, it would be tension would be equal to Fc plus mg, which is mv squared over r plus mg. This is the equation we're going to use to find that angular speed. This equation here, where we have tension is equal to mv squared over r plus mg. But we have a problem. The question asks for angular speed. This equation has linear speed. They are two different things. So how do we convert this linear speed to angular speed? Well, you could work out the question and find v and then convert v to the angular speed, or you could just incorporate angular speed into this section here, and then you don't have to convert at the end. I'm going to incorporate angular speed at the beginning instead of at the end. So how do we incorporate angular speed into this equation? Well, let us do some working out. Omega, which is the angular speed, is equal to angle swept out divided by time. So omega is equal to the angle divided by time, right? Now, we want to convert this to linear speed. How do we convert omega to linear speed, right? Well, angle times the radius of the circle gives us the length of the arc swept out by the angle. The length of the arc swept out by the angle is going to more or less give you the linear speed, right? Or the linear distance. So that linear speed would be the length of the arc swept out, which is the theta times the radius. And then because this is the distance and we want to find the speed, we just divide it by time. So you can see here that we have omega times r divided by t is equal to v. And up here we have omega. Up here we have omega is equal to theta divided by t. Now you can see that this theta divided by t is the same as down here, theta divided by t. So we can say v is equal to theta divided by t, which is also omega up here. So v is equal to omega, and then we write the r. So v is equal to omega times r, or r omega, depending on how you want to look at it. Now let's get back into this part. This part has mv squared over r. This part is, this part here, v squared over r. We previously talked about that. We said that v squared over r was equal to centripetal acceleration. So how do we convert centripetal acceleration to a form that incorporates omega? Well, we know that v is equal to r times omega. So if we have v squared over r, all we need to do is say the centripetal acceleration is equal to v squared, which is this, so it would be r omega all squared, divided by r. So it would be this, right? So then we square the top of the equation, so we get r squared omega squared over r. So now we can just remove the r from the denominator and remove the square from the top. And we get centripetal acceleration is equal to r omega squared. Now that we have centripetal acceleration, we can basically substitute the r omega squared for v squared over r, right? So this is centripetal acceleration here. We can remove this, and instead of writing v squared over r, we write r omega squared. So this is the equation that we said we were going to use, this one here. So it would be, rewriting it to incorporate omega, we would end up with something like T is equal to m times r omega squared plus mg. And then all we would have to do is solve for omega. So now we just plug in the numbers and then we solve for omega. The tension at which the string breaks was stated to be 20 newtons, so that's going to go here. The mass of the stone was stated to be 500 grams. 500 grams is 0.5 kilograms. And we're going to use the standard units when we do our calculations, because that's going to ensure that you get the right units in the answer. And if you need to convert the final answer, you can convert the final answer as necessary if the question states. But when you're working with the questions and you're writing down the numbers, you should ensure that you write them down in their SI units. So even though the mass was 500 grams, it is actually 0.5 kilograms, because 500 grams is equal to 0.5 kilograms. So m is 0.5. R is 50 centimeters. The SI unit for distance is meters. 50 centimeters is half of a meter. So it's going to be 0.5 meters again, times omega squared, which we're trying to find. And then we have plus mg. The m we stated before was 0.5 kilograms. And then g would be 9.8 meters per second squared. It would be 9.8 newtons per kilogram, but newtons per kilogram has the same unit as meters per second squared. So now we just do the multiplication. So we're going to get 20 is equal to 0.25 omega squared plus 4.9. Subtract 4.9 from this side. And then you subtract it from this side. Let's just write 4.9. There. So we subtract 4.9 from this side, and we're going to get 15.1 is equal to 0.25 omega squared. And then we divide this side by 0.25 and do the same over here. The 0.25s on this side cancel, and we are left with 60.4 is equal to omega squared. And now we just have to find the square root of this side and then the square root of that side. So we get 7.77 is equal to omega. Now, what is the unit for omega? The common unit for omega is radians, which is a unit for the measure of an angle per second, right? You could also write degrees per second, but if you write degrees per second, you are going to have to convert 7.77 radians into degrees. And then that answer that you get when you convert the 7.77 radians into degrees would be your answer in degrees per second. After doing all of that, you would have finished the last part of question number 4. And if you would have done all of this working out and the explanations, then you would have acquired 15 marks. That is going to be it for this past paper questions video. Thank you all for watching, and I hope you've learned something.